Welcome to a new video in our series, A Beginner's Guide to the C Programming Language. In our last video, we discussed how to work with files, the different file types, and perform operations on files. Today, we will discuss dynamic memory allocation. The ability to allocate memory dynamically allows programmers to reuse memory efficiently, especially when the size of the data set is not known at compile time. You can also use it to create data structures, which are containers used to store large amounts of data in memory. Please like and share this video, follow our channel, and subscribe for notifications on new videos. In this session, we will cover the following topics: memory allocation functions like malloc, calloc, and realloc, and finally the function to free the memory, that is free. Why do we need to allocate memory dynamically? Very often, data requirements are unknown at compile time. So you cannot allocate memory in advance using static allocations as in variable declarations. Also, if you have a large data set that needs to be processed, then dynamic allocation can be used to allocate memory for the data set, process it, and release the memory once the data set is no longer required so that it can be reused later on. Finally, dynamic memory allocation can be used to create complex data structures or containers that enable efficient storage, quick retrieval of data, and efficient sort, search, and other operations on them. The memory allocation functions are malloc, which are used to allocate a block of uninitialized memory from the heap, calloc, which is used to allocate a block of initialized memory from the heap, realloc, which is used to reallocate memory for a previously allocated block of memory, and finally free, which is used to free this dynamically allocated memory back to the free pool of memory. All these functions are declared in the header file stdlib.h. The malloc function takes one parameter, which specifies the size of the memory block to be allocated, and returns a pointer to the starting address of that block of memory. If the memory could not be allocated, then malloc returns null. Note that all the memory allocation functions make system calls to the operating system, since the operating systems also manage this resource. Also, the function malloc returns a void pointer, so it needs to be typecast to an appropriate data type. As can be seen in the example here, we allocate memory for 100 ints using the function malloc. The returned pointer is typecast to an int pointer type. If malloc does not return null, then each element of the int array is initialized with an incrementing value. Notice how we have used the base index form of addressing here. We could use both the base index form of addressing as well as the indirect form of addressing. This is because the pointer arrptr is considered to be the starting address of the array and the index is a number that is calculated from this base. The function calloc is also similar to the function malloc. The only difference is that it returns the starting address to a block of memory that is initialized to 0. The realloc function is used to reallocate a larger or a smaller block of memory to a previously allocated memory block. The two arguments to the function are the pointer to the previously allocated block of memory, followed by the new size of the memory block. The function returns a pointer to the new block of resized memory. In the example shown, the previous block of memory is for 100 ints. Then the realloc function is called to reallocate memory for 200 ints. Finally, the free function will release the dynamically allocated block of memory back to the heap. After the function free is called, the pointer to the memory block should be initialized to 0 and not used anymore because this memory is no longer allocated and may be allocated to other variables later on. Let us see an example of dynamic memory allocation and how it works in practice. The program shows a book record structure that is type def to create a new user-defined data type. We then declare a pointer to the book structure and dynamically allocate memory to one structure. The structure is then initialized to some constant values using the structure pointer and the arrow operator. Finally, the data in the structure is displayed on the standard output device, and the program terminates. We will use the debugger to walk through this program. The variable book PTR initially contains a junk value because it is not initialized. Note that if pointer variables are used without proper initialization, it will result in an undefined area of memory being accessed. This will result in unpredictable program behavior. Here the book pointer is initialized with the return value of malloc, which allocates memory for one structure of type books. The return value of malloc is checked for the value null. If malloc has not allocated the memory required, then nothing can be done further, so the program exits. Look at the watch window as we single step through the initialization statements and the print statement. This is the output of the program. We have reached the end of this video. Please follow, like, and share this video, and click on the bell icon to receive notifications. In the next video, we will discuss different types of data structures and operations that can be performed on them. I will see you then.